In the name of Almighty God, I'm Mahsa Hassan Koshi, and today I want to talk about the electromagnetic waves beam envelope interface, or EWBE, which is a physics interface in capsule multiphysics for simulating light propagation through devices where the electromagnetic field amplitude varies slowly over wavelengths. It works by decomposing the electric field into a rapidly varying phase function and a slowly varying envelope function, allowing for reduced mesh size and efficient simulations of devices like waveguides and lens systems. The interface is part of the wave optic module and is suited for unidirectional and bidirectional propagation problems. And how it works. The first one is field decomposition. The physics interface assumes the electric field can be expressed as a product of a slowly varying envelope function and a rapidly varying phase function, where k is the wave vector. The second one is simplified simulation. By prescribing the rapidly varying phase function, the interface solves the wave equation only for the slowly varying envelope function, significantly reducing the computational resources needed. The next one is meshing. This approach allows for a much coarser mesh in the direction of propagation because it only needs to resolve the variations in the envelope, not the full wavelength variations of the total field. When to use it? The first one is waveguides and optical devices, ideal for simulating devices where light travels in a known direction. The next one is unidirectional propagation, effective for modeling beams propagation in a single general direction. The next one is material nonlinearities, supports the inclusion of material properties like intensity dependent refractor indices. And what is the alternatives? The first one is full wave simulation or electromagnetic waves frequency domain interface. Used when the field amplitude varies significantly or when dealing with complex scattering phenomena into multiple directions. Through this requires a much thinner mesh. The next one is ray optics module, applicable for systems where diffraction effects can be neglected and the wavelength is much smaller than the device dimensions. Total internal reflection, or TIR, is a phenomenon where light completely reflects back into its original medium rather than passing into a second medium. This occurs when light travels from a denser or high refractive index to a less dense, low refractive index medium at an angle of incidence greater than the critical angle. The critical angle is the specific angle of incidence where the refracted ray would be bent at 90 degrees from the normal. Conditions for total internal reflection. For total internal reflection to happen, two conditions must be met. The first one is light travels from a denser to a less dense medium. The incident medium must have a higher optical density and thus a higher refractive index than the second medium. The next one is angle of incidence exceeds the critical angle, the angle at which the light ray strikes the boundary must be greater than the critical angle for the specific pair of medium. And what is the key concepts? The first one is denser medium, a medium with a higher refractive index where light travels slower. The next one is less dense medium, a medium with a low refractive index where light travels faster. And the next one is critical angle, the minimum angle of incident at which total internal reflection begins to happen. And what is the examples and applications? The first one is diamonds. The high refractive index of diamonds leads to a small critical angle, resulting in multiple internal reflections that gives diamonds their brilliance. The next one is optical fibers used for data transmission. Optical fibers work by using total internal reflection to guide light signals along the fiber. And the next concept I want to talk about is counterpropagation. What is a counterpropagation? Actually, a counterpropagation wave is a wave that travels in the opposite direction to another wave, such as a laser wave or a water wave, often in a shared medium like a fiber optic cable or a water body. These opposing waves interact to create phenomena like standing waves, Bragg solitones, or other dynamic effects, and can be utilized in technological applications such as optical switching, slow light devices, or even in the propulsion of underwater vehicles. Example of counterpropagation waves in optics. For example, the first example is laser cavities. Two waves propagate in opposite directions within a laser cavity, creating a standing wave. The next one is nonlinear optics. Counterpropagating light beams in a nonlinear medium can lead to all optical switching or the formation of Bragg solitones. The next one is spontaneous four-wave mixing. In a process that generates photon pairs, the four interacting waves can move in opposite directions. The next one is in fluid dynamics. The first example is water wave. Counterpropagating wave occur in water, sometimes leading to unique phenomena and interactions that can be studied using Hamiltonian mechanics. And in acoustics. The application in acoustics, the first one is radar irradiation. Counter-propagating waves are generated in absorbing media at interfaces when a radar wave is reflected back, creating waves that travel in the opposite direction to the refracted wave. And what is the application in biomimetics? The first one is fish locomotion. Some electric fish use counterpropagating waves in their fins for maneuvering. And what is the key characteristics and applications? The first one is standing waves. When two waves of equal amplitude and frequency travel in opposite directions, they create a standing wave, a stationary wave pattern. The next one is interactions. The interaction between counter-propagating waves can lead to novel phenomena such as wave attraction in Hamiltonian system or breaking of symmetry in nonlinear optical cavities. And what is the technological uses? These waves are used in creating slow light devices, optical polarizer, and are a subject of research in underwater robotics for generating force. And here you can see that I have used electromagnetic wave beam envelope or EWBE modules as a physics module and a simple rectangle here. And the property I have used are perfect electric conductor, initial values, match boundaries condition 1 and 2, and impedance boundary condition. I have used a wavelength domain for a study, and after that you can see the electric field perspective view and a standing wave here. Thank you so much for watching my video until the end. You can download this simulation from my GitHub as Masa script, and the name of this simulation is console beam envelope reflection.